In the previous video, we took a look at improper integrals where the interval of integration was infinite, right? Now we're going to take a look at the type of improper integrals in which the function itself has an infinite discontinuity on the interval of integration. So the interval itself is going to be finite, but the function becomes infinite, right? So let's write down the definitions that we need for these types, right? So integrals of functions that have an infinite discontinuity right, at a point within the interval of integration. So within the interval of integration are improper integrals of type 2. So these are the type 2 ones, and there are only two types, right? So that should make you happy. So our improper integrals of type 2. All right, so again, by infinite discontinuity, let me sketch the three possibilities here. So let's say A to B, and then at B the function has an infinite discontinuity, right? And again, we want to know, is that area there finite? So as I get closer and closer to that infinite discontinuity, does the area approach a number, or does the area become infinite, right? So it could look like that. There's your interval A and B again, and then maybe the vertical asymptote is down here. Now at the lower limit, so you could have a situation like this. Right? Now as far as, in fact, let me go ahead and shade these so you're clear as to what the area is that we're looking at. So that one, now here the function crosses the horizontal axis. Now we know that the region is always between the curve and the horizontal axis. So it will be here. And this is all good. But then as you get closer and closer to A, where the function goes off to negative infinity, then you end up with this, continuing indefinitely. And the question is that net area, finite or infinite? And then the other possibility is where you have your A and you have your B, but then you have a vertical asymptote, or your infinite discontinuity, right inside the interval. Now, there again, if you remember from Calc 1, as thinking of your one-sided limits that either go off to positive or negative infinity, there are different ways this can be drawn. I'm just going to draw this one way to say, let's say, from both the right and the left, the function goes off to positive infinity, right? So in that case, that would be the area under consideration. Right? Again, is it finite or is it infinite? Right? Well, in order to answer this, much like the previous in the case in the type 1 improper integrals, we have to come up with a two-step process. We're going to come up with an area function. That's the first step. And then the second step will be the limit of the area function. All right, So let's write down the definitions that we need that pretty much outline the process for each of these cases. So the first one, if f of x is continuous on the semi-closed interval a to b like that, or as an inequality like this, right? And we say semi-closed because it includes this endpoint but not this endpoint. So this is where we're going to have the problem. In fact, it's the middle one right here, right? So if a function is continuous on that interval with, and this is key, with an infinite discontinuity at x equals a, so like this, right? Then, so this is what we're going to do. So these are sometimes harder to spot. These are sometimes harder to spot because you don't really see a plus or minus infinity. You have to look a little bit more closely to determine if the function has an infinite discontinuity. And that's where we're going to rely on some of our work done in Calc 1. But what we do in this situation is, again, we're going to use a placeholder. Now, because both of these are like numbers, right? We're not going to use A or B. We're going to use C as the placeholder. And since the function has the infinite discontinuity at the lower limit, I'm going to put the placeholder there at the lower limit, right? And we will be able to evaluate this using our fundamental theorem. So what we're going to end up with is an area function in terms of C, and then what we're going to do, so let me put it on this the sketch right here. So it's like this will be my C, and then I am going to approach, I'm going to let C get closer and closer to A. It's like I'm inching my way closer and closer to A, but I'm approaching A from the right. So it's actually a one-sided limit. So it looks like this. And we're going to let our C approach A from the positive side, right? So this will be our area function, or in general, net area function. Right, so this will be our area function. Right, and we compute this first, right? And then we take a limit at the end to see, again, if our area function approaches either a fixed number, or does it either oscillate or does it diverge, right? Okay, so that's that one. Number two, very, very similar. If f of x is continuous on, again, another semi-open interval, but now it's on this interval a to b like that, or where a is included but b isn't. Why is it not? Because that's where it's going to have the infinite discontinuity. So with an infinite discontinuity at x equals b, then how is this one defined? Well, if you follow the procedure from the first case, we're going to replace the x value at which the infinite discontinuity occurs, and that's where we're going to put our placeholder. So we're going to now go from a to c, f of x dx, right? And then we are going to let, so before I write the limit, this is this first case here that I drew. So we're going to put a placeholder there, and we're going to come up with an area function for that green area, and then we're going to let C get closer and closer to B, but that will again be another one-sided limit, and in this case we're going to approach B from the left, and we're going to see what's going to happen to my green area as C gets closer and closer to B from the left, right? So it looks like this. The limit as C approaches B minus. Again, this is going to be our area function, or step one of our process. Right? And we're going to evaluate the limit of this area function, and that will tell us if this integral, this improper integral, converges or diverges. And 3 now is like the one that's in the middle, and what we do there is we split it into 2, right? So if f of x has an infinite discontinuity, an infinite discontinuity at x equals c, where c is some number between a and b, so like this, right? And we want it to be continuous at every point except at c, so and continuous on the interval, the union, so from A to C, open, union, open, C to B, then this is how it's defined. So the integral from A to B, since there's that vertical asymptote between A and B, again, the fundamental theorem wouldn't apply. So I have to split it up, and I have to express it as a sum of the first two cases. So first, you would go from A to C, f of x dx, and then from C to B, f of x dx, and then basically combine the two procedures from parts 1 and parts 2. All right? And the terminology is the same as that we introduced in type 1, so I'm not going to restate it. But if these limits are finite, then we say the improper integral converges to whatever number the limit ends up being. And if the limit does not exist, then we say the improper integral diverges. All right. So let's see if we can get a couple examples of these in. All right, so the first one is something that looks like this. So it's the integral from 0 to 1 of 1 over 1 minus x dx. Okay. And again, some of these are a little bit harder to spot, right? But if you notice, this function has an infinite discontinuity at x equals 1. I know that because at x equals 1, I have the form 1 over 0. And that's the form, thinking back to Calc 1, that leads to an infinite discontinuity, or in fact, an infinite limit, right? Where a function goes off to either plus or minus infinity, right? So we'll just say this. This function has an infinite discontinuity at x equals 1. So since it's at the upper limit, we're going to use that procedure. We're going to put a c there. Now, do we have to put a c? Actually, no, we don't. We can replace it with the typical upper limit b. It's just that when you're writing down the general procedure, because you don't have numbers in there, you already are using A and B, and so you don't want to replace B with B, right? But if you wanted to, we could certainly go ahead and use the more familiar upper limit, right? And this is what it would look like. So here's our step 1. We are going to evaluate the area function, and the area function is 0 to b, and here's my function, 1 over 1 minus x dx. So we need to find our antiderivative, and this will be ln, but here's this -1 coefficient in front of the x, so it's going to be negative the natural log of 1 minus x, and that's evaluated at 0 and at b, right? So at the upper limit, just plug our b in, we'll have negative the natural log of 1 minus b, and then now there's a negative sign here, so when I subtract the negative, I end up having plus the ln of 1 minus 0, which is 1. But the natural log of 1 we know is 0. So this ends up being our area function. So negative the natural log of 1 minus b. Right? And again, in terms of what this area function, what it looks like, so we have our 0, we have our 1, so we know the function is going to have a vertical asymptote there. Now, as this function approaches 1, or I should say as x approaches 1 from the left, then this denominator approaches 0, but from the positive side. So actually what happens is you end up having a function that looks like this. So this is the sketch of that function. Okay. And what we're doing is, by putting this placeholder, there is our b, right? And again, this function now says for values of b that are, let's say, close to 1, if I wanted to find the area under my original function, the 1 over 1 minus x, I could plug that number that's close to 1 in here, and it will give me the green area. But the question is, what happens as I let b get closer and closer to 1? And that leads us to step 2, right? The whole idea of something approaching a fixed number, well, that's the basic concept of a limit. So let's look at step 2. We have to evaluate the limit, and now it's the limit as b approaches 1, but it's 1 minus, right? Because we're approaching 1 from the left of this function, this negative natural log of 1 minus b, our area function. Now this negative sign, it's a -1 that's multiplying the natural log, and we can pull the constants out, or the constant out of the limit, just like we can for an integral, just like we can do it for a derivative. So this is negative the limit as b approaches 1 minus the natural log of 1 minus b. Now, as b gets closer and closer to 1 from the left, 1 minus b approaches 0 from the right. So what we end up having is the natural log of 0. But as you approach, as as your variable, or let me say this, as the inner part approaches 0, the log approaches negative infinity. If you think of your log graph now, your log graph has a vertical asymptote at x equals 0. And in fact, it goes off to negative infinity, right? So this is negative, and this approaches negative infinity. So those two negatives tell me now that my green area, as b gets closer and closer to 1 from the left, this green area is actually infinite, right? So let's kind of summarize this. So the improper integral from 0 to 1 of 1 over 1 minus x dx, this improper integral diverges, right? And a way to think about it is, this whole idea of it diverging is, let's say I actually wanted to paint this region green. There is not enough paint in the universe, and there will never be enough paint in the universe that would allow me to paint all of this region going indefinitely upwards, right? So that one diverges. All right, let's take a look at another one. Again, something that the actual calculation isn't very difficult, right? But just to emphasize the subtlety and what is expected in terms of what needs to be shown in this process. And again, it's a two-step process, right? So let's take a look at number 2. And this is the integral from 0 to 1 again. And I'm going to take a function that's very, very similar to this one. I'm just going to take the square root of the bottom. So the square root of 1 minus x dx. This function also has a vertical asymptote, or an infinite discontinuity at x equals 1, right? So that's what makes this improper. So I cannot use my basic fundamental theorem approach, because that theorem says your function has to be piecewise continuous or continuous, right? Which this function is not, right? So this 1 over the square root of 1 minus x has an infinite discontinuity at x equals 1. So the procedure is going to look very similar. So here's our step 1. We're going to find the integral, so replace the upper limit here, because that's the value of x at which the function has the infinite discontinuity. Replace that with a placeholder b, and then everything stays the same. I will, however, rewrite the function so that I can integrate it. And this is 1 minus x to the negative 1/2 dx. Now, this one looks like, a U sub would work. And I want to show you what it looks like to do a U sub where you have this placeholder as your limits. Doesn't really change the process, but it's good to see what it looks like. So let's let u equals 1 minus x. So that means du is negative dx. I don't have a negative sign here, so I'm going to multiply both sides by negative 1. So I get negative du is dx. All right. So far we have, this is our u, and then we just figured out that dx is negative du. Now let's figure out what the limits look like, right? Because we should be able to convert this entire definite integral, this area function, we should be able to express it in terms of u. So when x is equal to 0, u is equal to 1. Right? And then what about the upper limit? Well, when x is equal to b, well, just plug b in. Then I have u is 1 minus b. Yeah, so this will become 1, and this expression becomes another expression, 1 minus b. Right? So even if we have a symbolic integral where the limits of integration are not numeric, or instead symbolic, we can still convert everything over in terms of u. So the integral now goes from 1 to 1 minus b, and then we have our u to the negative 1/2, and then we have a negative du, right? So this is a product. Let me make sure that we're multiplying. But that negative sign can be taken all the way and put in front. So let's go ahead and do that. And then let's integrate u to the negative 1/2. So that's our power rule. So we're going to add 1 to this power. That's going to give us 1/2. And then I have to divide by 1/2, which gives me 2. So this is negative 2 u to the 1/2. And then that has to be evaluated at 1 and at 1 minus b. And because I switched everything over in terms of u, right, I can just evaluate this, and then that will give me my area function. So I have negative 2 there. At the upper limit, I'll have 1 minus b to the 1/2. And then at the lower limit, I'll have 1 to the 1/2. Right? So in fact, yeah, let's simplify this. So I'm going to write this as the square root of 1 minus b. This is 1. And then let's distribute the negative 2. So I have negative 2 square root of 1 minus b. And then I have negative 2 times a negative 1. So that's a positive 2. In fact, we can write it like this. 2 minus 2 root 1 minus b. Right? So this is the area function for this 1 over 1 minus x on the interval. Now, what's really interesting about this is that when you look at the graph of the 1 over root 1 minus x, it looks very, very similar to the previous one. Very, very similar, right? So this area function would give the area over 0 to b under that function, right? Again, it's a function because we don't have a specific number there, right? And then, step 2, take the limit of this as b approaches 1 from the left again, right? So that's our step 2. So step 2, we have to evaluate our limit. And now this is as b approaches 1 minus again, but now we're going to take this. So we don't have a ln like we did. What we end up having is a root. So it's the limit of 2 minus 2 root 1 minus b as b approaches 1 from the left. Right? Now, as you approach 1 from the left, 1 minus b approaches 0 from the right. So it's like you have a 0 plus under the square root. In fact, that's sometimes a way you can sort of indicate what let's say the 1 minus b is approaching. So this is a constant, it doesn't change. The constant multiple doesn't change. And then we have the square root, and what we have here, so essentially what you have is 1 minus 1 minus, and remember what this minus here is saying is that you're very, very close to 1, but less than 1. So that difference will be very, very small, but positive. So you end up having 2 minus 2 root of a small positive number. And it continues to get smaller and smaller. So that's why we don't put like a 0.1 there or a 0.01, because that's not what's happening, right? You're not taking the square root of 0.1 or any fixed number for that. You're saying what's going to happen to this square root as the number under the root gets smaller and smaller and smaller, but continues to stay positive. Well, that square root will approach 0, right? So what happens is we end up with this. So this is 2 minus 2 times 0. So this improper integral actually converges to a value of 2, which is really remarkable. I mean, you look at both graphs, they look very, very similar, but one ends up having infinite area, whereas this one, right, if my upper limit gets closer and closer to 1 from the left, then the area is going to approach 2. Pretty remarkable, right? So let's summarize that. So the improper integral from 0 to 1 of 1 over the square root of 1 minus x dx, this improper integral converges to a value of 2. And the thing with the improper integral is because it involves, well, this two-step process of the area function and then evaluating a certain limit, it's hard to always say how it's going to end up. Now, with experience, you'll get a sense of when things will converge and when things will diverge. But the process is that set procedure that will make it very clear which is the case. So sometimes it's not always possible to tell just by looking, but we rely on the precision of, again, the step 1, which is our calculus step, meaning evaluating the antiderivative and then using our fundamental theorem to come up with this area function. And then the second step, now we say, well, what happens to that area function as our limit approaches whatever specific number, or in the type 1 case, approaches plus or minus infinity. All right? And I'll see you in the next video.